Hey, Coffee Compiler Club here today to talk about compilers and where compiler guys get their exercise and whether or not they love Scala. I'll try to do something with Scala. I don't know. I'm working with a guy who's doing a bunch of, well, Derek's doing a bunch of stuff with Clojure, Sea of Nodes with Clojure. Boy, that was um, it's not as fast as you might like to believe, or as the Clojure guys would have you believe, meow.
Hmm.
So, hey, Arthur. Um, I have
Hello.
a weak starting suggestion I'm going to roll with unless somebody wants to say something now. I'm going to hit the doc share. I'm going to talk lattice theory, which is not everyone's favorite thing. And I got here in an indirect route. Let's see here. Going to clobber everything. Yeah, okay. So the I got playing with lattices again because of type function pointers. So in the land of yak shedding, bike shedding, how the hell did you get here? Somewhere in the universe, I have a well-working thing that says something like, I have some struct s, I make a definition for it, uh, and then I make a variable, oops, and I say, let's do capital S for my struct here. The little s is null, and then the program goes on, does something else. Okay, well, this is fine. So then I come along and say, oh, I'm going to make a function pointer. And I need a type for a function pointer. So I have a typing language, just like you would do in C. You can have a function type. So there's my function type. I'm going to make a variable function, and I'm going to assign it to a null because I haven't got a function for it yet. So that's where I started from. This throws a type error because null is the type of pointers to structs, not pointers to function code. Oh,
Why
gee,
no has have a type?
How do you pronounce that variable?
function.
Oh, okay.
What would you like me to put? I can put
I
B
like you
bar
calling
Baz.
it function. Just thought it was funny.
I mean, it's just a variable name. I mean, I Baz, right? Whatever. But this is a type error.
Why no does have to have a type?
Exactly. Why is null having a type? Well, it does because that's part of how the lattice goes. And null has to land in the lattice so I can do all the normal things you would do with types, including the top-down version of the universe for global sparse conditional constant propagation, basically.
Hey,
Okay.
does it mean that different occurrences of null will all share the same properties? Is it based on the first context where you encountered it?
No. So I'm coming up to my solution. So
Okay.
the current solution is there are no function pointers in simple. Therefore, this problem does not arise. And null is a member of the type of pointers to memory, pointers to structs, pointers to arrays. Arrays are just another struct in simple. So this was, and then the equivalent for ints uses a different syntax, right? So 0 is the initial value for an int. It's not a null, and null is not an int, and int is not a 0, and null is not a 0. Blah blah blah. They're two different things. Now, I didn't want to make another type. Like you can imagine, oh, I have the null function type or something evil as a type name. I was like, no, that was ugly. I want null to be like a null.
Hmm.
Okay. So what am I doing here? So I threw up I have the current simple lattice up through chapter 18. I was going to get the short version as a reminder, do the big version quickly, and then show you what I ended up doing. So the kind of things that goes on in lattice for this compiler work, they are a lattice, they are bounded, so fixed height. They are symmetric, which means you above and below the center line, it's a mirror image. Symmetry gives you this interesting property that the sparse conditional constant propagation results are provably identical as the provably fixed point you at a better solution than the bottom-up versions. Um, I have worked with lattices that were not symmetric in the top, and you can get to funny peephole situations where people will take advantage of some partial information that you can't get another way, and then you get work order dependencies whether or not you optimize. So that got fixed uh, by making the lattice symmetric. That hit me at C2 a bunch. Hey, Derek. I'm doing lattices. This actually directly impacts us on your project very shortly here.
Okay.
We're not there yet, but it's going to come up quick. This is function pointers. So quick go around. Here's a struct s. I can assign it a null. We're all happy. The variable s, little s is a null. Here's the type of a function pointer. Here's a function. I'm going to assign it a null. This gives me type error because null is a type memory pointer. It's a pointer to memory. And I don't want a separate function pointer null, although I imagine could. Of course, integers have their own null. It's just 0. Fine. So I fixed it in the lattice. And that's why it impacts us, is because I think this lattice, we're going to fall into this before long because we're going to do functions here. So the simpler lattice from the earlier times, just ints top and bottom, tuples top and bottom. Tuples will have black types, which are the endpoints and everything in between. So this is any other type included other tuples or whatever. The one currently in simple looks like this. So highlights, ints picked up a range. That's the angle brackets, square brackets of high and low. This lets me take things like this is a bool, and ints and shorts and bytes for networking byte buffers and crap. Control picks up a top and a bottom instead of single control. It's a little more type safety, has no semantic use. There's floats, 32 and whatever. There's pointers, which have a null, allowed, or not. And then they point to a struct. And structs have fields. And two structs can be the same if they have the same fields in the same order, and fields have names. And then they have a type out here on the right, which I put as this shaded int pointer thing, which in the next slide I'm going to call scalars. And then there's a memory, which actually has more precision than I show here because I tell you what the memory types are. So I know what contents of memory is. So, and then they're broken up by aliases across the middle here. So all private alias classes, I'll tell you exactly what's allowed in that alias class. So this is the new chunk of the lattice. This is only a middle piece. So I'm going to look at the ends real quick and go back. So here's scalar at the bottom and anti-scalar at the top. And going back, scalar picks up the top and the bottom will be the above of int, float, pointer, and function pointer. And the scalar will be the bottom of int, float, pointer, and function pointer. So let's go back to this thing for a second and talk about what it is, because it does a weird thing with null. And the weird thing I worked out in AA a couple years ago, and it's kind of a mental bitch to wrap your head around, but it fixes the null problem. So at each of these ovals, the top piece is a convenient name to give you a hint. And the bottom piece is a list of either ands and ors of the kinds of things that are allowed. So starting at the bottom, it's the most obvious one. A scalar is any int, and you can replace int with float because, and in fact, this lattice shows two things, so it doesn't get too complicated, but the floats and the function pointers live in this same lattice in the same vertical line. Just replace Tmp with Tfp. Fine. Scalar then has ints, type memory pointers, floats, type function pointers, and 0. Some nillable thing. And here the trick is, if you don't say nil in your type, you don't allow nil or a null or a 0, however you want to consider the value. So an in scalar is a not null scalar value. It's some int, some float, some pointer to memory that's not null, some function pointer that's not null. Here's the normal bottom ints, which includes all 1, 2, 3, 4, 5 to billions and 0. And nint, not null int, that's an int you've already tested for null and proven that it's not. Pointer, that's all the pointers, including null. So you could argue I should put the abbreviation version up top here as temp question mark, saying pointers to memory that might be null. Whereas an intemp is a pointer to memory that's proven not null. And simple does this proof not null like right now and does a good job. And so when you write code, the compiler knows whether you have a null or not. He doesn't allow you to write code that might null pointer accept. So that's kind of nice. And then going around, I'm ignoring the two guys in the middle. Those are the excitement. So going on the edges and going up, I have the inversions of all the things below. That'll show up when you do any sparse conditional constant propagation when you start high and work your way low. in particular, if you started at type top and you fell to X scalar or anti-scalar, it means you're some scalary value that would fit in a register, a machine register, but I don't know what it is. It might be a null. That's the plus null, plus zero. It might be an int. It might be a pointer to memory. I don't know. And then you fall down and say, oh, here it's clearly not a pointer. It's definitely an int, but it might be a null or it might be any int. I don't know yet. Might be a constant, might be a range. I don't know. And you fall down here to say, oh, I know it can't be a null, but I don't know what the integer is going to be. This is the version that says I had to compute the value. This one might yet turn into a constant. So same thing on the pointer side. There's a choice of a null plus zero, and then there's you must have a zero. That's included. Then we get to the weird things in the middle. So nil is the easiest one to think about here. This says you have a zero. And you might later pick up, you might have a choice of any int, any memory pointer, any float, any function pointer, but you're definitely a null. And so that makes this guy, this pink dude, fall in the lattice to ints with null or pointers with null or function pointers with null or floats with null. And that makes this nil the thing that I want to use here. Oops, here. Because that nil will work, and again here, that nil will work in all contexts. Let's say this nil, actually, let me just cut and paste and say, go down a chunk. I can put nil here, I can put nil here, I can put nil here, and this is no longer a type error.
Yeah.
Type function pointer, type imp. It's a valid int, it's a valid float, no type error. I think, Bill, you're about to say something?
I was about to ask, I've been thinking a little bit about this composite type idea, and I wonder if the nil fits in that way.
What's a
Like,
composite type?
well, maybe can I share my screen and I'll show you because I pulled up my lattice here, which looks a lot like your lattice, but it's a bit different. So you'd share.
Yeah, okay, shared now.
Okay. So I think you can see this. Let me just resize it.
Oh, you got to grow it a bunch.
Yeah. So I've got sort of similar. Let me just get rid of the extra stuff here. So top, bottom, this is the scalar.
Yeah,
But my
anti-scalar.
symbolism is a bit different from yours, but
No, it's just my X scalar or my total scalar versus scalar.
twiddle scalar,
Right. Yep.
right. So this is something that I used, and I had this very complex representation of floating point before. So I had like this, it was like, oh, it could be 8 sized like an FP8 or an FP16. And then we have like two flavors of floating point. We have like the where we move the mantissa. So you have like a
Yeah.
range version and a precision version. So that's
Yeah.
this. And then we also can have it be on the RISC core or in the PE array. And
So
then
for people
there's
who are
also like,
listening, the PEs are effectively a DSP chip intended to do high volume, low precision FP math.
yeah, yeah. So, and then we also have like the ability to put a constant in it. So, but I don't have ranges. So it's just
Yeah.
either you don't know the value or you know it.
Yeah, I did the range thing because it's a lot easier looking and the code is a
Yeah,
lot simpler. And it
yeah. So
covers your
for ints,
size.
ranges make sense, right? I just couldn't
Okay.
figure out how, like I
Yeah.
couldn't understand how you could do a range for floating point and have it actually make sense.
Oh, I see. Yeah, maybe. Fine.
So, if maybe someday I could do it. So then I had this idea that I could do the same thing for int because we've got some annoying stuff. And right now I'm not even representing some of it in the lattice, but I sort of was working on the design. So right now I've got like the range and then I've got the domain, and those are the two pieces that I have. But then I also had this like idea that I have like two's complement or sign magnitude, which
Yeah.
is this really annoying distinction that I need to maybe keep track of, probably. And then we have like 4 bits, and then you have to know which side are we on, the left or the right, basically.
Right.
And then so I had this idea that I would like switch my ints over to this. I haven't done it yet. But couldn't we like extend this with another another like box here and do like the nullable stuff? Like couldn't I do like I'm not sure. It's like nullable.
Well, right. So on the question on the inside is a little less interesting, except specifically when you're doing like Bool test optimizations where you know somebody's tested for something, and so the Boolean is always true now, always false going forward, and then the test repeats. For the pointer side, it's big news because a bazillion people do things with pointers that are null or not. In
Yeah.
the domain of the problem you're solving here, you have very few pointers and they're almost never going to be null. So I don't know that it's exciting to do. It's just like,
I just wonder if structurally this
yeah.
idea could apply here and simplify the idea, even if you did it like as like at the
Yeah.
scalar
So,
level.
so this doesn't solve my problem, but it
No?
highlights it instead. So any nil on ints is just just the version of zero or not the zero. I allow a null or I don't. You
Yeah.
have a nil, sorry, an int flavored nil, and you have a lattice around the int flavored nil.
Yeah.
Okay, I have a lattice around int flavored nil. I have a lattice around int flavored uh, uh, pointers to memory. Then I need a lattice around int flavored pointers to functions. And as soon as I do that, I need a different constant for so the parser can tell when I write the constant for the nil, am I writing an integer nil or a memory pointer nil or a function pointer nil? And that
Uh-huh.
requires syntax out of the parser to tell.
Oh, right, because it could actually be it's sort of at a different level.
That's it. Right, 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 right.
So
If we
like
go back
you
to
can
my
be
lattice, I can show you where those
but
things show up
so
already. But go ahead.
so I'm still not 100% convinced because like I have this like domain thing here. It is also present in scalar. And like as I could be any scalar and I could know it's in the PE and or in the risk. And then, you know, I still know that domain aspect. And then when I go to int, that travels with it. And so it sits
Right.
here, but it does travel around.
Yeah.
And so I could be in this state and be in any state.
What I said was for nils. The domain problem for people listening, that's whether you live on the risk or the DSP side. The domain problem lives and could in fact be better solved by putting it in the lattice, kind of what you're hinting there. Then you
Yeah,
wouldn't
that's what
need
I
the
do.
domain pieces in the int or the FP or the PE side because they would show up overall on both sides, which is totally reasonable. And there is
Yeah.
a lattice where you could put the domain in and have it remain a lattice. And then you would get rid of the any domain, unknown domain, and the int and the PE, instead put it on and I think that makes more sense actually. You,
Yeah. Because the like I could have a scalar include its domainness as sort of an intrinsic
yeah,
characteristic of the scalar, just like, and I could do that also for the int and also for floating point. But I had this sort of idea a long time ago that I could just have a separate lattice, and then this thing is this composite of two lattices, and then here
yeah,
could become a composite of 5 lattices or four, and here it is actually like for floating points it is currently a composite of 4 lattices.
yeah.
So
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 let
the
me throw something for the audience here.
complexity of that lattice for floating point was so high. I was having such a hard time creating the my meet function.
Yes,
And then when I finally was like, let me try this, I got the full representational space and these 4 very simple lattices. And so when I meet
yeah.
a floating point, I just do 4 meet of the component pieces and it
Of the
works
tiny
perfect.
components. Yeah. So let me fill in for the audience here. So the lattice for the constant propagation wants to be bounded and symmetric, and a couple other things, commutative, reflexive, whatever. There's a couple properties that documented elsewhere. You can get this by a couple ways, including what Derek's doing, which is simply taking a node along the center line and exploding it into a parallel element-wise pile of separate little lattices. And that's a known strategy that I routinely use. So if you go back to my big diagram, which we don't have to do right now,
Yeah,
you'll see
I can
that
stop sharing because it's all I really had to say with this.
no, I think it's fine. And I think your domain question goes sort of straight to the heart of where you would go do things with lattices here. So if you look at this, the aqua floats, it's just a simple box that internally has been exploded into float parts. And if you look at memory here, you could imagine a single boxed element and it's exploded into memory points. And that goes true for all of the different lattice element pieces there. Um, and then Matt's saying LLVM has a notion of you're on a GPU versus a CPU. I think that's a reasonable. Yeah, right.
On
So,
on the
so
LVM, you basically have like a number which is called address space. By default, it's usually 0, but you can say, for example, address space 5 pertains to that GPU. Because if
right.
you have a pointer that is a GPU memory as opposed to a pointer that is a CPU memory, and you wouldn't want to mix them up.
You wouldn't want to mix them up. Yes.
Or you want to track when you assign the data from one to another.
Yeah.
And it's just
Yeah.
a number.
Azul had a stack addressing space where you could have addresses that had a bunch of other fun bits in the pointers, pointer stealing, but it was a stack address valid for that CPU. And you couldn't let another CPU get that pointer because it would refer to his private stack space, not the main shared memory. There's definitely different address spaces. Yeah, and that's completely, doable here. Like I have my top and my bottom and pointer to pointer. If this pointer or these things come over to the scalar, these guys at the scalar place here picked up a parallel new piece, which was address space, risk versus PE. And there's a bunch of PEs per risk, so you would have which ones you're talking about.
Well, for me, I just think of them as all of them.
Yeah, I know. And maybe that's all we need too. I'm not clear yet if we need to break out the different PE pointer address space pointers or if that makes sense. Maybe it doesn't. Maybe they all point to the same shared CRAM. It's all fine. Anyhow, all I did after this, what I ended up with is this nil thing, and I don't claim the syntax for nil is good or bad, but it does allow me to have a nil value that I can put in the parser as a single parsable token and have it be type safe in all directions. And in fact, the math works out. So I'm in the middle of finding all the places where I was doing things that I should have done a different way. But I'm up through like chapter 13 or 14 now of things. I have a few more bugs to fix, and then this will be done. And then the
I'm gonna
code
stop
looks.
share here.
Sorry.
I think we're back to your lattice, so it'd be better to see that rather than mine.
I'm showing you my lattice.
No, I said I'm gonna stop sharing because we're talking about yours, not mine. So it's
Oh, I thought you said you were done and you stopped. You saying we had parallel shares going on and I didn't know. We could have been. I only see my lattice. I don't see yours.
there's no screen share right now.
Okay. There's no there are other people seeing my screen, right?
I
Yes.
see. Yes,
Okay.
I see
Yeah. Thank you.
cliffs.
So I heard you say no screen share. There should be a
okay.
screen share.
Okay, sorry. Yeah.
Fine. Yeah, fine. So anyhow, that was my hack this week when I wasn't working on Derek stuff. I currently am using nil just so it spells differently, so I get all the errors for having the spelling change. But I have a single token I'm going to put here, and I can put null here, and I can allow a 0 here, except that I'll turn it into a null under the hood, and that's fine. And null again, or nil, or perfectly validly null here, which is like, that looks weird. But that's where I'm headed with this thing, is it's almost done. So you'll probably get this, and null will appear here, and this will be valid because null will be actually this nil in the lattice, which will be a valid member of function pointers and structs or memory pointers. And that was my, that was my either that or burning my house down. That was what I did all week.
I got a question. Cliff, why do you need null by itself? What's the difference between, it seems like null is
Okay.
valid in fewer places than nil. Is it you want something that means int 0? That's what nil can mean if you assign it to an int, and then it just seems weird to let int equal null if it's not a pointer to something, or what's the
Well, okay, so the issue here is that I had a type error going up to the top block. I have a type error here. Yep, type error. That's what I wrote. That's because
Yes.
null, prior to chapter 18, null is a memory pointer, not a function pointer. Cannot assign a null to a function pointer variable. Okay. What do I put for a function pointer variable that means I got a null, I don't have one? Like in C, you just put a null there, literally, because it's outside all the type domains. So, what is the thing I put here? I want to be sort of precisely typed. So I came up with a version of null, and now I'm using the word nil only to distinguish it from the prior old null. It has no other reason to be called nil. It might as well be called null as well. So I came up with this
Okay.
nil thing, which is this element in the lattice here, the pink element, which is valid in all these contexts. As soon as I have it valid in function pointers and memory pointers, it's completely symmetric, and there's no reason for it to not be valid everywhere. And whether I present it to you at the where you write it, in the code internally, in the simple code internally, it's going to be a nil. And then that cleans up tons of code, it turns out, because there's no distinction between all the different nils, and a bunch of places where you carefully picked apart and distinguished, you no longer care. So if you look at this guy here, I say Tmp down the left-hand column, I say int down the right-hand column, but they're symmetric left and right. So if I just take int and replace it with float, I added floats in here. And if I take Tmp into the TFP type function pointer, it's completely symmetric. It just flows in on the left-hand side, just like Tmp. So it makes no difference. So as soon as I have the pattern where I allow Tmp and TFP, it turns out it's trivial, and it's actually simpler. It's less code, less implementation to add ints and floats as well. These vertical columns, you might as well replace int with Tmp or TFP. It doesn't matter. They're completely symmetric. The green and the blues are just completely symmetric. Just replace all the ints with pick your flavors of whatever things you're putting in. I don't care.
I ask you to repeat something you said, I'm sure earlier, but I was struggling with it. My phone keeps thinking I'm driving, and I can't. It won't show me anything. So the four columns, what are each four? Like just one column, like the green column on the left, like the bottom completely
right.
null, and the
Right,
one
going from the bottom
null.
up, it's memory pointers or a null. So before I use that memory pointer to grab a field out of it, I need a test for null.
Right. Okay.
Then
That's
the
bottom.
intemp is no null. It's just a pointer I can immediately load from.
Okay.
The twiddled version is the high side, or the sparse conditional constant propagation high side. It is some function pointer, but I don't know which one, and it is one that the compiler yet has a choice for.
Okay.
This will show up when you do analysis around a loop where you don't know what the back edge is,
Hmm.
but you don't want to lose precision. So you fall in with something that's probably a low pointer, but when you look at the loop and you're trying to do analysis around the back edge, you don't know what the back edge is going to be. You're going to pretend that it's going to be some high pointer, any choice of pointers, so that it doesn't disturb the value that it doesn't lower, reduce in the lattice the value you have coming in.
Hmm.
And you're hoping that that's correct, and you'll find out later. So standard conditional constant propagation kind of stuff.
Okay.
And then the next higher one up is the same thing, except that null is one of the choices. you might be null all the way around through the loop, top to bottom,
Right.
in and out, back and forth. Could be a null everywhere. Don't
Hmm.
know yet till you finish the loop out.
All right.
So the bottom one is you definitely have a null, and if you want to use it, you gotta test for null. The next one up is you have a concrete pointer. You have to get it by computing it from somehow, but it's not null, so you can use it once you've got it computed, but there's no shortcuts on getting it. The next one up, it's not a null, but I don't know what it is. It could be some constant pointer. I could even completely constant fold it away. I don't know. It could be any possible constant. I could hope it to be a constant that I got from some other place, and when I merge it in a phi function, it remains a constant. This is only interesting around loops,
Mhm.
but it happens. Fine. And then the next one up is the same thing, except that it might also be a null. And that actually, works out really well in loops where it's all nulls, then you basically usually just constant fold it away and it disappears out of the code and life goes good. So that's the left-hand side going up. Replace everything I said with TFPs and you get the same thing. The bottom guy is some function pointer or null. I have to test for null before I can call it. Next one up would be a function pointer that is not a null, so I can just call it directly. The next one up is some function pointer that I don't know yet, but it could be a constant. It could be, that would be really exciting because then I could get rid of the indirect function call and put it with the direct function call, static function call, and inline it, right? There's performance gains to be had if I get a constant out. And the next one up is the function pointer or null. So maybe it's just a null and I'll have to have a null check anyhow, but the null check will just constant fold away and it'll be like, there was no function pointer. So no
Mhm.
codes, no call, there's nothing. It all just collapses to zero and disappears. So that's the going up on the green side. You go
Yeah.
up on the blue side, it's perfectly identical, totally symmetric. Just replace the three letters I and T with TMP, TFP, FLT. Makes no difference.
Yep.
Except conceptually, you think ints instead of memory pointers. Does that?
Yeah, but you know what I find interesting about this, and that's why I'm still coming up to speed on your lattices, is if you take those two columns and you sort of stick a mirror in between
Yeah.
them, like horizontally, that they're kind of mirror images. The null, the one that might be null is the farthest away from the center. It seems kind of interesting. I have intuition as to why. Like I get why having it at the bottom or null. Well, I don't know. I mean, I'm not sure why this goes in what direction, but definitely the mirror image kind of is interesting to me.
If it's any
But
consolation, I wrestled with this lattice for at least 6 months, always thinking there was something that I was missing or didn't get how I wanted it. That in particular, I always wanted to put nil on the center line, and then I would put anti-nil above the nil, and you would fall into it. That seemed plausible. Like, why do I need anti-nil? If I don't have anti-nil, it turns out I don't get a lattice. If anti-nil points to nil, I don't have a lattice. That one took me, that was a big chunk of time before I proved that you could not have a lattice if you had a distinguished nil. If you have a distinguished nil, you cannot have a lattice. So that's a bitch. That defeats a lot of things. So you can fake all kinds of stuff, and C2 did, and C2 I never got this sorted out. And as a consequence, there are situations where some combination of peoples and constant folding will make progress in one work list and not on another, one work list order and not on another. And then there were some hard cutouts where I would not be, I would fail monotonicity and then force it. Like, no, this is bullshit. And force and the forcing would cause a hard fall in the lattice in the constant propagation domain. And you just gave up optimizing something. You just like, I give up now. Having a real lattice stops that. And also, I mean, it just simplifies things. I don't have any special cutouts for like, oh, fuck, how did I get here? Stop and just, fall to bottom and walk away.
So what do you mean by anti-nil? I see it there in blue. And I
Yes.
see the guy on top over here, like tilde temp,
Yeah.
is pointing to it,
Yeah.
which I think means he's above him in the lattice, more towards the top. Okay.
Yeah.
And the
Meet,
arrows are going down, but
right. Meet says fall down in the arrows going downhill
yeah.
until you came to a common place, the highest common place.
Okay, so that's actually your high going up the lattice is actually going down in your diagram.
No, going down in the lattice is down in the diagram.
Okay.
You follow the arrows all point down.
Okay.
And then the pink and the blue, the light blue, they are side by side to remove the notion that one is ahead or behind another, or above or below. They are same level in the lattice, just kind of hint to you that one is not above or below the other. And there's a slight change in how the arrows go. One has two arrows in, one out. One has one arrow in, two out. This remains a lattice and a Hesse diagram. Like if you wiped out all the coloring and all the letters and just had a bunch of nodes and edges, this looks exactly like one of the wiki pages on lattices for a Hesse diagram. Fine. It's a valid lattice.
But how would you
Does
describe
the
tilde nil? I mean, it's like I have I have something I don't know. It might be a constant, but I don't know what it is. It could be many different things, but it can also be nil or null.
Yeah, so what it means is I have given up on claiming that it's any I give up on it might be a constant pointer, it might be a high int, it might be a constant of some kind. I've given up on that. And then there's a choice of a null.
Hmm.
So
It might
maybe
do
it's a
that.
null. So this is okay. So here's the key intuition for me. This one took me forever. I made a lattice. I had to follow the math. The math demanded I have an extra node.
Right.
Now I'm trying to find a reasonable meaning for the node. Turns out that when I run these constant propagation, turns out it also shows up when I do like stupid dead code loops that comes out of the fuzzer all the time. You have while loops, you have huge spinning fuzzy dead loops. You get dead loops, you get this all the time. So this node happens. Now it's never in any valid final answer. It always folds into something else. But in the middle, you get this all the time. So what is an intuition for this node, this aqua bright blue node? So we're trying to put an intuition on it. And I have my guess of an intuition, but it's kind of not like anything
It
reasonable.
sounds to me like it's I don't know what this is, but it could be null.
That's
That
the
one is the one thing
pink
I
guy
know it
is
could be.
null.
To me, it
Well, I know, but
sounds.
this could be null. This one, that
Yeah,
any of
there
them
is the plus zero means it could be a null, or it could be
something else.
some hard concrete value, which is a scalar.
Hmm.
But I
Doesn't
won't
this?
know that it's an int flavored scalar or a pointer
Right.
flavored
Yeah.
scalar or a float flavored scalar. It's
Yep.
just some scalar.
That's what it means. You just described it. I think that makes sense.
Okay.
It's interesting to me that it works out that way on the lattice. It seems a little. I
So
mean, there's something there.
my reading and my suspicion, I'm just how I'm thinking about this is that it means that we've figured out that it's null. We just don't know what type it is. So
Yeah. It's not quite, it is null. It's a plus zero. It may be a null, or it may be some scalar value that's not null, but I don't know what scalar value. I can't tell you float from int from pointer.
uh-huh.
Yeah,
So
you
it could
didn't
be
have one
null,
that is,
or
you don't have a node that says this is null.
yeah. And when I go down in the lattice, I always throw away a choice. So when I drop from the bright blue and I go to in scalar, I threw away the choice of it being null, and now it's just some unknown, fits in a register, not null value. I have no idea. And what can you do with such a thing? Well, you can null check it, but that's literally all you can do with it, right? It's no longer a valid. It's not a pointer. It's like I had a trinary if test that simply said some untyped variable x is some random predicate and either 17 or pointer to struct. Okay, what can I say about this x thing? It's either 17 or pointer to struct. Turns out I can type that. Well, whether or not the code's valid or not, I can type it. And the type is in scalar. It's a not null scalar value, and I can null check it. And the twiddle nil version is one where, like the in scalar version is one where I know it's not null, so a null check would just say, oh, it's always not null, and I would fold the test away. Whereas the in scalar version says it might be a null, and it might be, it might be this in scalar guy. And because it's above the center line, it will still fall before I'm done. And that will turn into maybe I get to null check it. I have to null check it, or maybe it goes to the black scalar at the bottom, and I must put the null check in as opposed to the white in scalar where I don't bother with the null check. I know it's not null. So if you do an if on it, I'll just say, yeah, true.
So in the lattice, null is a type.
Yeah.
Yeah.
I'm calling it nil for the
Because
moment just to distinguish
because
it from.
if we see in the docs, the null is on the right hand side, so it should be a value. So there is a new value and a new type.
Yeah.
So
Yes. Yeah. Yeah.
hmm,
And in the code, which I could probably show, I'll show you.
yeah,
I
on
throw
the
that
if,
nil
if you
around
switch on
all.
the docs, if you switch on the docs, the null is on the right hand side of the
Yeah.
assignment because and the hunch is that it should be a value. If you put it on the left hand side where the type should be null, so that
You can
and
put a type there. It's a valid. It's a valid type. It doesn't make a whole lot of sense. I can do
mm,
no q. Okay, to only be given the value null.
but,
That's a valid type. That's okay.
okay, so far so good. But what's the type of the queue? The type is null. Yes.
No, yeah, literally.
Yeah.
It is.
Okay.
It is. It
Yeah.
is. Oh, come
It's tricky
on.
because it makes sense. The next question is: do we have exceptions in simple? What
We
would happen if I
we we currently do not have exceptions.
what would happen if I reference the value q or the
You get a
the
compiler
function?
error that says this will be compile error, compile time error.
That's a great.
Hmm.
I think it says might be no.
I think the
Okay, if it's a
$1 billion
mutable, if it's
wasn't.
a
Oh,
Okay,
sorry.
wait.
no,
Too many people
Okay.
talking.
go
I'm gonna
ahead,
say,
Bill. Go
No,
let
ahead,
me
no.
Bill.
finish.
Go ahead, Bill.
Oh, I was just going to just point out that I think the $1 billion mistake wasn't putting null in, but not having it checked by the type checker.
Yeah, so it is simple. In simple, it's always checked by the type checker. You're not allowed to write code that might null check on you. So this is this case here. I have some S, I have some unknown Q, I do some random predicate, and I either put a null in or I say new S. Okay, so what is Q null or not? Well, randomly according to the input, it is. So then I say Q dot X, right? So I want to return Q dot X, and this will fail compile error, right? That currently goes on.
The same goes as just referencing q, not a
Yeah,
field in
no,
S.
Q can be referenced because it could be null. Like you could say if Q exact. In fact, the obvious thing here is to say something about if Q, and then inside of if Q, do
Even though
this,
it's not null. Even though it's not
right?
null. Yes. Okay.
And then this is not an error, and the constant, the lattice lets me flow
Hmm.
that this flows, Q test for null here, and Q is known, not null. That works right now, and I could cut and paste and clonishly make it for type function pointer happen the same way by having a private function pointer null from the memory pointer null. But then when you try to write a null for function pointers, you have to use a different syntax because, as I said in the very first box, the current status is null is a memory pointer. It's a specialized memory pointer.
Hmm.
And therefore not a function pointer, and therefore that's a type error.
Okay. How should we think about the null? It's not an uninitialized reference type.
It's not
It's
uninitial. That's correct. It's not an. It is an initialized reference type. It's
hmm,
initialized type.
but it doesn't point to something. So
Right. It is. I think Cameron likes to say it's a subclass or subtype of all other types. It's not really because it's a lattice, so there's not a subtyping notion per se.
so you say it's a null. S for example, it's a null. So there is a pointer to S. There is a memory, but it doesn't point to initialized S or something.
No, in this middle block where I'm using nil,
Hmm.
let me throw my nil in here so we're clear. I'm trying to figure out if you're talking about the before or after situation. In the after
Hmm.
situation, um, the nil or zero is just syntactic sugar. It doesn't matter to me. You can write it in both ways. I can also put zero here. It's all that's syntactic sugar. It's you got the type in the lattice or you didn't.
Hmm. 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 Hmm.
So now it's what it is a thing which is could be any of the different flavors of other types, and it's the null/zero flavor of all of these other types.
Hmm.
I don't know, does that help you? You ask again because I'm not certain I answered your question.
Mm, I think it got the right kind of words in the answer. Okay. If the function is mutable and later change it to something.
Yeah.
Okay.
Some function type expression goes here, and then it's going to be if function, and I can call it.
Okay, so why initialize it to null? Why
Because I don't
can't you
have
just
one.
leave it can you leave it an uninitialized function?
Nothing is like Java, nothing is uninitialized. So you'll get the null initializer if you don't say anything.
Hmm.
So similarly, just up here where I leave it uninitialized.
Mm-hmm.
Okay, that'll be null.
Mm.
Just so you can't accidentally have an uninitialized variable. So simple does not allow uninitialized variable references. And you get a nil. If you
Yeah.
didn't say something else, you get a nil.
Yeah, okay. I'm not quite sure if there is some distinction between the null or uninitialized. Yeah, is there a benefit to be on null?
Yes,
but just
because I want to be able to test. I want to not have you take an uninitialized value and reference memory through it or call it as a function pointer.
Mm-hmm.
Right.
Mm.
So if I don't say S is a null up here, and I say come along and say S.x, so replace S with person,
Mm-hmm.
replace X with bank account, and then someone says I make an uninitialized person, and then they say print, S dot bank account, S dot X, which is your bank account. This should crash at the compile. This should be compile time error. This should say, no, you didn't initialize S. It's not that I accidentally picked up some pointer to some garbage memory that by careful work of a hacker as pointing into probably a bunch of people's, and he finds a people and sucks out a bank account from somebody.
With the same success, you can track uninitialized person S and throw a compiler.
Yeah, right. Exactly. That's exactly what nil is doing here.
Hmm.
It is tracking the uninitialized state by saying, I'm going to initialize it. So you could track uninitialized per se. I found that inconvenient as a general programming model. Just fucking throw a nil down, and then you have to do a nil check, but you never get uninitialized memory. It just still seems too much of a security hole to allow an uninitialized and then have to test for uninitialized everywhere.
We do have a primitive in simple. If you int x, the not the capital one, but the smaller I, does it signify a primitive or something?
Yeah, it's a primitive. Yeah.
Okay, so you can or you cannot say no, or if you say no, it will initialize to the default value.
Yeah, it'll initialize to the default value. Yes.
Okay.
In the pre-chapter 18, the default value was an integer 0 for ints, for floats a float 0, for pointers pointer null.
Yeah.
In the chapter 8 version, it's just null because it covers all of them.
Okay.
And of course, the hardware representation is just a pile of 0 bits in a register kind of thing or in memory.
Okay, I think I kind of get what it's going on, what it's supposed to do.
What it's supposed to do, yeah.
Hmm.
What it originally supposed to do is just let me get rid of this type error right there. That one was bugging me.
Yeah.
And then the other thing going on here is I want a function type expression here, but I don't have it parsing yet. I said, I'll first do a type of a function pointer and I'll write a program with it and see if it works. And the answer was I couldn't make one work.
The tricky bit is to decide what null really means. Is it a value inside the domain of the type or something else?
Yeah, right. So is it a value in the domain of the type? Is a question that I wrestled with for a long time, and it's kind of a red herring. Um, it's not that it doesn't matter. You follow the lattice and you don't fucking care.
Hey, I have a question about the lattice here.
Yeah.
It shouldn't be a diamond, not like a column, because you said that you would like as you go down visually or follow the arrows that downward, you get fewer choices. But the bottom two have go in the opposite direction. It seems like you get an extra choice between the bottom one compared to the one above it because it could be null.
So it's not a choice. That's the tricky wording. It's a wording problem here. This is you must deal with a null. You can't tell at compile time whether or not a null shows up. So at compile time, you better be able to handle a null there. Here, you can tell at compile time that a null can't show up, but you don't know if you're going to get a pointer or an int. But you have to deal with ints and pointers. But you don't have to deal with a null. You do have to deal with ints
Right.
and pointers.
Yeah, well, it seems like a sibling. Those two in the middle seem like siblings.
Well, that's why I put them in the middle, side by side, because they're siblings.
Well, they're not side by side. They're one above each other, I thought.
Oh, two in the middle? Wait, which middle are we talking here?
There's a
Oh,
column. Sorry, I can't see the screen right now, but you have a column. I'm visualizing it. I memorized it. No, I didn't memorize it, but you got a column on the left. It's either green or blue. I can't remember.
yeah.
And so like A is above B and that's above C and that's above D.
Yes.
And what it seems like is B and C should be not related to each other.
Okay, the
And
column
they're
on the
the
left
center.
and the column on the right, blue or green or whatever, they have this funny relationship. One is above the center line, one is below. Above the center line is only shows up when you do things with like dead infinite loops or sparse conditional constant propagation.
Yeah.
And
Okay.
below the center line meant that I had some code, it computed a value, I have to deal with the value I got computed. Above the center line means I might get any possible value. The compiler hasn't chosen what it's going to be yet. It
Right.
could be as convenient as a constant, and immediately constant fold everything completely away.
Right.
I have this common example I hand out to people as an example where people mix up I want to say uninitialized or unbound or whatever. I'm going to write some code here. It won't be too long here.
Could I show my screen real quick? Because I was looking at this diagram and I have an idea that might be interesting to show.
All right, yeah, because I'm busy trying to write some stupid loop to kind of show what uninitialized means here. Should be a share, yeah.
Oops, shared the wrong things.
But then I want to look at your thing and not type code.
Yeah. Okay. So here. So I redrew your diagram. Sorry, I didn't do the colors.
That's bad.
Yes.
But I laid it out a little bit differently, and I just wanted to show you something that if you rotate it,
yes,
there's a rotational symmetry if you draw it the right way.
Yes, it is.
So
I'm using .graphviz. I could totally fiddle enough with graphviz and get my rotational symmetry in.
Yeah, because like you have this here, and it's at the same level as this guy, or
no, but it's intended to be in the middle. Go down even again between temp and intemp for both of them. Get them side by side.
But they're not side by side. That's the thing.
No. Put them side by side.
Okay.
And okay, now you're rotationally symmetric.
But I was already, because look.
Yes, but you're also rotational symmetric if you're side by side. That was what I was intending. And then GraphViz says, no, I'm going to move you up a little bit. Like, fuck it. I can't fiddle forever with GraphViz.
Yeah. So you think they should be here? I was thinking that they should be like this because this is where...
In all my paper diagrams, and I have many, they look like what you just drew. This is where I started my intuition from for a long, long time. Putting them side by side broke in my head the notion that one is actually higher or lower than another, which got me away from this sort of broken thinking about what anti-nil means. Having said that, it's perfectly reasonable to go to the model that you like, which is the model I used for many years. Yeah, they're perfectly symmetric.
Yeah. So
and then deal with, nil should be low, and it points down into one of the not nil or the nillable temps and ints. It's all good.
Yeah. So like, because it sort of has a stronger connectedness down here.
It
This
does.
one has a stronger connectedness up here, and they would be in the middle if they
Yeah,
didn't
but you
completely
cannot draw a
overlap.
line between them. That was part of the hard learning for me. You cannot draw the line in the middle, or you are not a lattice anymore.
Yeah.
So now here's another trick, and this maybe goes to somebody else's commentary. If you got rid of the labels for a second, I don't say do it now, but if you could imagine getting rid of the labels, you can also drop the bottom layer of scalar, temp, int, and nil, and you'll get a cube. And many times the valid lattices I deal with have cubes. Like leave in scalar, put in scalar back where you had it, get it
Like,
polite. Oops, nope,
oh,
unwind, undo.
no, it's okay. I've got to
Okay.
undo. So,
Well, the problem is you lost the cube notion. That there is a cube in many of these things.
uh-huh.
And the point of there being a cube is that there are three symmetric properties you're choosing yes or no on. Two to the, yes or no is two choices. Two to the three is eight. That makes a cube. So here's an example. So go to scalar at the bottom, and nuke that node. I'm going to nuke the bottom layer in the cube. Nuke Tmp on the left. Nuke int on the right. Okay, nuke nil. We're missing. I probably nuked the wrong thing. I was trying to get a cube out of it. There's a cube in there.
Is there?
Yeah. Oh, maybe not in this version. Don't line those up. That's like painful for me to stare at because I lose all the things.
Right.
I still see a cube when I look hard.
It's almost cubic.
Yeah,
I've been trying to look for
this
these
lattice
shapes
is
too, and
not.
finally gave up.
I have done plenty of lattices that I could see various kinds of nested cubes or hypercube relations.
Yeah.
Because you had two to the four, two to the three, choice of things. Like when you add a domain in, you'll get a hypercube flavor because you'll add a thing parallel to scalar that everybody participates in, whether they're
start by putting ntemp and tilde ntemp over each other and nint and tilde nint over each. Nope, down instead.
down.
In
the middle.
Yep.
Yeah.
Now drop n scalar down. Or yeah, sure. Drop n scalar down. That one goes up a little. Sorry, that one goes up, and the tilde n scalar goes down. There's
a cube.
There's your cubic double cube.
Yes. And then you could there's two cubes and you screw around. I was trying to get rid of the bottom cube just so the top one would be more obvious.
Mm-hmm.
Yeah. Yeah. And it's basically a lattice says I have three things I'm taking choice on.
Yeah.
And because I want to allow all of them. If you do this kind of thing, there's a special term for the lattice. I want to say distributive, it's not it, but there's some special term here meaning this lattice is sort of trivial in a bunch of ways. You can imagine having a bit vector of 3 bits that are just on or off, and then the lattice meet is just or the 3 bits or and the 3 actually or the 3 bits. It's like, oh, okay, fine.
Starts to look like the F cube.
The lattice implementation I ended up with in simple version is way the hell nicer than the one I came with AA, but I claim that's the second system effect where I dealt with thinking about the problem a little cleaner, a little newer, and accepting the thing about nil being not, you can't have an edge between twiddle nil and nil.
Sorry,
you missed a lot of stuff there.
Lambda cube is what I meant. Sorry.
I'm sorry?
There's the lambda cube.
Oh, the lambda. That's not far off. It's another kind of a lattice thing. All right, I'm going to finish out my little piece of dumb code here. You missed all the fun lambda, fun things, Cameron, with lattices, which we'll probably come around to here.
I was dealing with snow. Our first snowstorm of the season.
Excellent. Okay, so I have this little C-like program.
Can you share?
Oh, yes, I can share if I can get myself to it. How about now? How about now, Brian Cow? Okay, the bottom.
A little bit zoom.
There we go.
To see it.
Is that not readable?
Somebody pasted something.
By the way, Cliff, I think I found the name for that. So in data flow analysis, there is lots of problems called the bit vector problems.
Yeah.
Also, it's locally separable problems. So I think that's what you got.
Oh, locally separable. Yes. And I want them each to be locally separable. And that's what led me to having X now. So in this program down the bottom here, if you were to go optimize it as your in your head as your best LLVM optimizer or C2 optimizer, what kind of code would you generate? In particular, are you generating code for statement one and statement two? Statement one, statement two could be anything. They could launch the missiles, print foo, whatever the statements do. They have side effects. They do crazy things, which means you can't execute them prematurely. So what does a valid, correct code generation look like for this kind of a thing?
Is this all the code?
This is all the code except that pred comes as some predicate function. You don't care what it is.
It's okay.
It's zero or more round trips. It
Mhm.
terminates, but you don't know how often.
So here X is uninitialized. The if test is it null?
Yep.
Okay.
Bummer.
So
This is like Arthur. Arthur, are you there? Are you paying attention?
Yeah, if we look at this from a LLVM perspective, you are reading uninitialized memory, which is undefined behavior, so it can do whatever. I think it should be. One question is whether we can prove if we actually go into the loop and use this uninitialized value.
Let's claim that you can't show what random will do other than it's going to give you a Boolean result 50-50. So you'll execute the loop some exponentially decaying number of times, but you will go into the loop.
I wanna say if it's a primitive.
Over and over, because I think your X equals 0, X equals 1 needs to be flipped.
So from like LLVM perspective, and in the way that it handles these kind of scenarios, you are reading, basically it's undefined behavior and the whole thing can be thrown away.
All of it.
All of it. Well, classic QB, whatever can happen.
Yeah,
it's unreachable code.
Okay. So for me, I come around to, and in the end, I end up with where LLVM is as well. For me, what I start with is I put some value for X, let's call it top N, and let me restate that. Let's start by saying I'm reading uninitialized memory. If it's going to be true, then you hit statement one, X is now true forever, and the loop never runs statement two. It runs forever on statement one, and therefore you don't need to compile statement two. Of course, S could be 0, in which case the opposite happens. You only run statement two and never statement one. And here it's UB, the compiler can pick. You're always statement two or always statement one. Or in the case of the Sea of Nodes, LLVM-ish, actually, constant propagation lattice game, X becomes top as an uninitialized value. Then as a top, I don't want to choose which way it falls until it's forced by some other condition. So he would say if top, which means I'm not going to do the statement one, and I'm not going to do statement two, and I get exactly what Arthur says. You throw all the code away. Neither one of them is executable. You throw it all away. So this kind of like Theodore, you're talking about, hey, just be uninitialized and test for it at compile time. It's a valid thing to have top values in sparse conditional constant propagation.
Okay.
And I don't want it to be confused with uninitialized memory. So
I think
there is a thing here where I want to instead say, I'm going to initialize that value, and I'll initialize it obviously to 0. And then, either you get initialize to 0, or you get a complaint from the compiler saying, I'm not going to compile this till you initialize it.
Well, you can if you move this into the argument, now it will become just some unknown value, and then I think you can do the whole thing as you described. And just what kind of meaning do you give to this uninitialized memory situation? It's a matter of like IR semantics or like programming language semantics, and then depending on the meaning, you then handle it differently.
When I was doing C compilers, I would never say a UB like this would cause everyone to get thrown away. I thought that was just too not in the spirit of what the compiler should do. So as a best effort, I would say, I'm going to pretend that you're given some value and I didn't know what I would give you. Bottom usually, and in which case you would get both S1 and S2, and you would get suboptimal code, but you wrote crappy code. So it would run, it would do some interesting semantics. It would be pretty obvious what the semantics are. No UB mystery, but not necessarily optimal.
Well, but then in practice, you would run into these kind of situations in a truly dead code. And if you are aggressive at detecting this kind of stuff and actually pruning this thing away because, well, I proved the paradox here, so let me throw it away. You might actually be gaining something. So it's an interesting trade-off.
In dead code, that's what I was talking about much earlier. I had a bunch of scenarios in the fuzzer producing dead infinite loops where you prove this kind of shit. And you get these funny, the twiddle null, the bizarre X nil thing. That one shows up all the time in dead infinite code, in dead code, yes. And you prove these paradoxes, and currently I throw it all away. I just don't allow you to write the UB in the first place, so I don't start with the UB, but I would definitely get the top value that would then show up in this infinite loop. And I would throw away both arms because X was top, but also all the entire loop. Whoops, that was not what I wanted. Hang on, Google. The entire loop would be dead at that point. I wouldn't get X uninitialized until it was already dead coming in which case the whole loop goes away as well.
Yeah, I think there is a distinction. Like you don't have UB in your language, but then in your IR and inside of the compiler, you will have these kind of things, maybe explicitly, maybe implicitly, and you will take advantage of this.
I will take advantage of, I'll have top, and I will take advantage of top. I will not have a UB, but I will take advantage of top. I want to distinguish between those two. The lattice element top appears in junk dead code, and you take advantage of it, but the user doesn't get a UB. Okay. Boom. Well, that was my week of experimenting with this lattice, and I fought with this lattice. I fought with this with AA for a long time, or for settling on this. And this particular version of it is a much cleaner version. Although if I went with Derek's route, I would have the aqua nil, the X nil and the nil be a little off center from each other. And that's not a bad answer, Derek. Like I said, I drew that way many years. Many times. Maybe a couple of years on I'm looking at a piece of paper a couple of years old, but I have this very thing all over it. Fine.
I remember you presented this a long time ago, and I was thought about this when I was doing my type system too, and if I wanted to put it into my lattice as part of what I was building. And I decided that I wasn't sure if I needed the complexity, and so I just decided not to deal with it for now. And yeah, so I'm still kind of wondering whether I need it or not, but probably will need it for things to be nice and well defined. And like you said, it simplifies other areas.
Sorry, Matt's putting up things. I have seen these a long time ago. Yes, where choices are made in favor of one or the other. And the answer was don't have this kind of non-determinism.
In Angelic, for example, you just choose whatever is declared in favor of the desired result.
Yeah.
So instead you can think of the compiler acting on undefined behavior and deciding, oh, we just pick any value. This value is the most convenient. Let's assume that it was this value.
Yeah. No, that's what top is supposed to be for. When you're doing a back edge around a loop, what is the back edge value? It's the most convenient value. But the angelic versus demonic is like an entertaining viewpoint for choices are made in favor of non-determination. Can I prove that this program terminates? Well, your demonic guy says, I'm going to try hard to make it not. Yeah. Interesting. Okay. Yeah, I've seen this before, but it's still, that's very on par with what we were just talking about with this guy here. Very much on par with that.
So you said you were wrestling with this lattice. So how is it different versus what you were looking at in AA?
Oh, this is where I ended up with in AA.
Oh,
but
okay.
the wrestle was, I just wanted a nil that could fall to a pointer, to a type memory pointer, Cameron does Tmp, or an int, or a float, or a type function pointer. I just wanted a nil that would fall down. didn't want the aqua do that. Like he has no semantic meaning to me at that era, at that time. So I wouldn't include him. I wouldn't even think to include him. He just wasn't in the diagram. So as soon as you take him out, you're not a lattice. And if you take him out and you draw all the edges that he would fill in, you become asymmetric. And if you're asymmetric, you have this funny problem that I would mention before, where you become work list order dependent of whether or not you discover a particular fact or not. You either fell down from TMP to this midpoint, but the midpoint didn't exist. So you started here and you're going to fall down to here in scalar, or from top choice int to in scalar at some point because you've got a bad program doing stupid things, whatever, or not. And if you hadn't fallen yet, then you knew that you were going to be some pointer or going to be some int. You did some optimization. Some people was valid. If you fell down to here, it was no longer valid and you didn't do it. And so you had this work list order dependent thing. Whereas if you took the fall would only take you to here, this aqua point that didn't exist. And then you would still be able to do the transformation and you get back your, I don't say, one-step church roster property. You would do all the right transformations and you would get the bottom-up p-poles and the top-down optimistic guys would always come to the same fixed point. Whereas if you missed out having this aqua node, you got work list order dependencies. You got to a transformation, before you lost knowledge. And the trick for all those transformations where they're only valid while you had some knowledge and you lost it is that you had to have a point in the lattice which held on to this knowledge. And this particular knowledge says, I am going to lose what the hell I'm going to get. It's going to be an int or a float or an int or a pointer because I'm writing stupid code. But I don't need to also lose the knowledge of it could be null or not. And so I throw away the opportunity to say, oh, if you happen to be mixing in ints and floats, or ints and pointers, it's because they're always null. And I've got a union going on, and the union just contains a null value, a zero, a pile of 0 bits, and I just have a 0 here. And then the conflict goes away. The mental conflict goes away. Somebody's got a union they put in C code, they wrote zeros in, they mem set to 0, and then they pulled a pointer out, or they pulled an int out according to whatever tag they hidden off somewhere else, except there's always a 0. So there's no conflict, and they don't get some sort of security hole or anything. It's all perfectly correct program. You lost that knowledge if you didn't have this aqua node in the graph. So I wrestled with that. And then I said, okay, symmetry, I'll put it in. But obviously, this aqua should point to nil because this should be above it and this should be below it. And I didn't quite yet have a notion of it's some mixture and I can't tell you which one. And this one it's a choice. It's either going to be an int or a pointer, but nary the twain shall meet. And I'll find out later as I fall in the lattice which one it's going to be, and it'll be correct. So, the one on the right is like, I'm doing type inference, and you haven't told me what type it is, but I'm going to find out by its usage patterns, and I haven't seen all the usages yet. So it might be an int, might be a pointer. Definitely going to allow null. And then later I discover, oh, it's a null pointer, or it's an integer value, just happens to be a null, whatever. So there was some intuition that told me this should have an arrow, the aqua edge should have an arrow to the pink edge. As soon as you put that arrow in, you're not a lattice. And I wrestled and wrestled and wrestled. I finally proved myself, oh, wait, my problem, and I wrote all this code, right? And the code would do things, and then I get these weird crashes, or this is a relationships fail, wasn't monotonic, blah, blah, blah. Crap was happening all the time. Finally wrote these hardcore lattice tests that Simple has, and they would fail all the time. I finally wrote a lattice explorer that let me build and tear down lattices repeatedly, fairly low cost, and prove they were actually lattices, and that my representation was minimal and got rid of the unneeded extra edges, and it cleaned it up. And I got these tidy, nice little diagrams. But then I finally proved myself, oh, but you cannot have this edge from here, from the aqua to the pink. I call that the crossing nil problem because I would cross over from this to this side, and then I would get these is a failures where I had a, pointer is an int is a pointer. It's like, no, stop. So I finally, once I gave it up and had to have this edge and had to have it not point to here, the problem's all cleared up. Then I was like, okay, what the fuck is this node? I have to have it. The math demands it. What is it? And then an intuition finally started to show up.
So in terms of implementation, is it like I assume there is no explicit structure like this in the code, but there are just implicit transitions between them that are written in the code.
I can show you what the code does. It's pretty straightforward. Like this implementation is now really straightforward. There is a. Go ahead.
You say I remember you told that you have various tests that check for the important properties.
Yeah.
I wonder if, like, purely from implementation perspective, if you can describe it in some kind of declarative way and maybe I don't know, auto-generate some of the code around it.
Yeah.
But on that declarative structure, if you can can have tests on the declarative structure and not on the effects of the execution. So you know straight away that the structure doesn't fit the properties that you need without like running a bunch of tests and hoping that you had a good coverage in your tests.
The tests have perfect coverage. There's only like 20 nodes here, 15 nodes. So I have perfect coverage on the tests.
Well, how do these tests look? Are they just snippets of code that make you go through some transitions, or they are more?
But they're okay. So in this giant lattice, every purple box, every node, not purple box, every node in here has 1 to 2 instances made as a list of concrete values that represent things that are going to be difficult. And because of symmetry, I only do the bottom half ones. So there's a 0, there's a 1, there's a 0 dot, there's a pi, there's like a 1.5 or something. There's a Boolean range.
You have your program like in AA that has these instances. Is this the case?
This is a standard test. Okay, so it is not in the test. It's not in the test harness. It is in the main code. The main code says, I produce a bunch of these constants or these interesting type values. Every type class, every Java implementation class lists a sampling of every interesting type it can make, which includes every node, every oval shape, whatever, every type up here on the bottom half and the center line, and I'll just invert them to get the top half. Then as part of startup and as one of my standard tests, I take the 40 or 50, it's actually several hundred now, constants, I throw them in a big array, I make sure I get the other half, so I do the dual, put them in a big array, and then I run a cubic test that tests all combinations. And because it's a few hundred cubed, it's like instantaneous, I don't care. But it covers all possible combinations in all directions, and it proves the properties that I'm looking for. So like I say, the code is very simple. I can show you the code. Let me just show you the code.
So it is exhaustive because
exhaustive.
Gotcha.
Okay. Type test is the one here you're looking for. This is the gather gives me a large collection of choices of things.
You're not showing the code, Cliff?
Oh, I'm not showing the code because I can't talk and run Zoom at the same time.
Just don't try to chew bubblegum.
And don't have me walk downhill either. I'd kill myself. View, appearance. Yes, appearance now. How about now? Here, 150%. Hey, here we go. Okay. Okay, so type lattice theory. Gather all the types. We'll look at them in a second. N squared loop, check commute, check symmetric, triple deep, cubic loop, check associativity, another triple deep, check another version of associativity. So what are they checking here? So commutativity is down here. It's T0 meet T1, T1 meet T0. They're the same. So that just said I can invert on the meet. There's a shortcut I do right here exactly for simple types because I don't know why. I could get rid of it now. I don't need it. Check symmetry. Check symmetry says this expression. If I have A meet B, I'm going to call it meet. Then the dual of A meet the dual of the meet should be the dual of A. And the dual of B with the dual of the same meet as I had before should be the dual of B. Ooh, but you pull these straight out of Wikipedia, it's pretty obvious what they're doing. Here's the meet. I call it MT, just like I wrote in my comments. Meet dual is dual meet. That's the D in front for the dual. T0 is D0. T1 dual is D1. The meet of dual meet and dual T1 and the meet here, and they have to be the same.
How does your let's say meet look like?
Okay.
Is there literally the structure in memory that you traverse, or?
Yeah, we get there. So meet does a bunch of things to optimize life. So the first thing is that if you're same, you just get out. Next type is if you're known to be identically typed classes. So this is runtime type information, or under type is a field, which is basically runtime type info. Then I go to an xmeet version where I know that I'm meeting two Java equivalent classes. Now the Java classes do not match one-to-one with the Lattice elements. In particular, these simple guys say things like, let me find the simple. Simple guy says, there's the whole bottom in the giant lattice, the whole top, there's control, there's X control, there's nil, and there's X nil. These are all considered simple types, but they don't necessarily land near each other in the lattice in a kind of way. They straddle top bottom and they straddle control X control, but nil and X nil are in the middle somewhere. So these are simple types. And here's my gather code, which says gather instances of simple types, then go to the nils, the scalars, the ints, the floats, the mems, the blah, and gather them all in a fucking big array, add all the duals. Now I have a giant ass array, run the triple cubic thing. Okay, so back down to where meet was. So there is a go to it where I know everybody's the same type. Nil says everyone's a type nil.
When you say everybody is the same type, can you give an example?
Yeah, you're both two instances of type float. So, or type int. You go to type integer xmeet, wherever xmeet is.
Right below meet.
I'm sorry?
I said right below meet.
Oh, yeah, probably. No, there is no meet.
Oh.
Meet is final. Going back to type, you don't overwrite meet. Meet is final. Instead, you go to xmeet, which I have 27 versions of. Here is xmeet for simple, and 9 overrides.
Mm-hmm.
And so for integer, xmeet says, I do a thing where I check the nil bit, then I take the min of the min and the max of the max of the maxes. And that means basically if I meet two integer ranges, their ranges just widen the endpoints. That's the meet of integer.
By the way, so when you do the gather, so there are some types that, let's say the integer type, it can represent different types depending on these high and lower boundary.
Right. So here are the
when
set
you do
of
gather, what do you put into that array?
Right.
You don't put all possible combinations, obviously. It will be just.
No, I put a bunch of samples, and we can argue.
Okay. Got it. Yeah.
So I put a signed sample, I put an unsigned sample, I put the Boolean, which is a bunch of special cases, and I put the max bottom, and then you get the dual of all of things. But I kind of voted that the int 16s look enough like either int 32s or int 8s that I don't need 16s in here, won't discover any new errors. There's no new code paths taken by int 16 that aren't already covered by int 32 or int 8.
So it's not that you're building an exhaustive structure in memory.
Yeah. But I would need the 4 billion ints versions.
Yeah, as you work through the program, you will lazily build the structure in memory, I guess, for the types that you actually need.
When I run the program, types are built as soon as I touch a class, a Java class. He runs the static initializer. Like I32 comes up in the static initializer, final static, int 8, int 32, u32, blah, blah, blah. These show up.
But then as you refine them through like meets or as you change them, you'll create new ones, obviously.
Yes. So the gather does at the beginning, it's just taking this fixed list of things. And the parser uses all the names mentioned here directly because they turn into user writable versions of integer types. You can just say, I want a U8 because I want a fucking unsigned byte, unlike Java. I want an unsigned byte. So I say, I want a U8. Yeah, fine. And the parser has some other syntactic sugar, like he gives you byte as a syntax sugar for unsigned 8-bit thing.
So okay, so xmeet will do the meet for the same type. That makes sense. How do you do the meets that actually move on the lattice?
So everybody who does nils goes to the type nil nmeet. So let's leave that for a second as the harder problem. For everyone who is simple, which is just those 6 things, top, bottom, control, nil, x nil, you go to the simple xmeet, not the subtype xmeet. And the simple guy just has an exhaustive set. Hey, if you're one of these, else if you're one of those, if you're nil or not, I might do something special here. Otherwise, you did a bad thing and I gave up on you. And bad thing meant I either went to scalar or to bottom. So if you mix control and nil, you fall to bottom. But if you mix an X nil flavored thing and a thing that can't have a nil, you're going to go to scalar. And you look at the lattice, you'll see it just drops to scalar. And then there's a few. So I'm triangulating and cutting out things. So if you're not a simple and you're looking at control, X control, and nils and X nils, and you're not a simple thing, then it's too late. You got caught above or you fell to bottom. And then the only time, then way down here, X control has a thing he does. So this is all just Carnot map. I'm cutting out chunks via tests to Carnot map and dive down. And then what I end up with is I'm meeting a nil or I'm meeting an X nil for type nils, or I'm into nmeet. So nmeet says I have 2 type nils, and if they are, there's an over, what's the override here? Oh, scalar, of course. I don't know how to go back now. That's not what I wanted. That's fine. So this is another triangulation. If the left or the right is a scalar type, so here is the structure. So you remember Bill keeps talking about my green column of 4 choices, or my blue column of 4 choices. Turns out if you look at the center of scalars, there's 4 more choices. X scalar, scalar, xn scalar, n scalar. So those are all done by extending off of type nil, which handles the 4 choices with literally 4 choices put into as a byte, a little type safety. I don't mix my bytes up because I have to cast fucking everything to byte. So I better mean a byte. And so this byte just takes on 4 values. I mean, I could have 2 bools, except then the code gets actually a little more complicated. The normal meet operation is take the max, and the dual is 3 minus. So those are nice. But this is an abstract class. So type int inherits from this, type mem pointer inherits from this, float and function pointer will shortly inherit from this, and scalar inherits from this as well. So I have to have a cutout for scalars. Otherwise, I'm mixing, if I'm in here, I'm mixing like a type memory pointer and a type int. And I'm going to do a stupid checks. I have an early lattice check. Like if I pull the lattice up and flip back and forth, you'll see. If you're both at nil of 0, if you're both at the twiddle temp plus 0 or the twiddle int plus 0, you'll fall to an X nil. Otherwise, you're going to fall down to an n scalar if I can prove you're not a null, or you fell to a scalar. So this is, again, I'm triangulating and cutting off all my options. Take that cube, do an if test, slice, now you got a square. Take the square, slice in half, oh, now you have, 2 choices, and 1 more test gets you. So there's a, log of 3, whatever, log of 8 set of choices, kinds of things going on here. It's not quite that tidy, but it's pretty tight. But this is about the implementation of that lattice as opposed to the code you see does not match one-to-one to elements in the lattice per se. Instead, the code you see represents if tests that cut the lattice in half.
Yeah, I wonder if there is a way to do this, as I said, in a more declarative way, where you don't need to spell out all these like specific cases and specific transitions.
Yeah.
Just because as it grows,
there surely is. I have tried this. My lattice exploring tool was me trying to do a declarative thing. It didn't look any better. And it ran a lot slower because I couldn't write the code. The code for meet runs a lot slower. That being said, having the lattice get fairly stable, there comes a point where I might go for like a large 2D array or 3D array where I just replicate endlessly, and then meet becomes pick one in each of the dimensions and pick another in each dimensions and you get the answer. Or a
Oh,
2D array where top
that's
and
a nice
bottom
way
come
to look
in.
at it. I think one thing that adds complexity is the fact that you don't have the exhaustive set of the types. Imagine if you had, then like literally you build the structure in memory, and then you literally traverse the graph and look for the proper node on the graph.
But I
But
can't build the exhaustive types because
yeah,
each
because
type
you
can
have
change.
the lazily created types, yeah, it's not gonna work.
Yeah, right, right. So yeah, there comes. You're right, right. It's implementation. Now we're all about implementation. There is a thing where I see many of the same types over and over, like over and over and over and over. So there's an interning step. The make eventually says intern. Everybody goes to intern. And intern says, hey, pull you out of an intern table. And if I didn't find you, put you, others return the old one. And missing in here, but showing up in AA, and maybe simple to get performance out is you just recycle the thing that if you got a hit in the table, you take the memory for the old thing and you return it and you fill it out later for doing it guy again. Because the interning table hits 99.9% of the time, like 1 in 1,000 times you come through and actually make a new type. Almost always you're just reworking the same old types you've seen before. So having a no memory consumed, if you pull something off a free list, you fill it out, you intern it, it hits, and you put it back on the free list. You allocated no memory. And the cost to do that was a pointer shuffle to get a thing from the free list, some writes to fill in some bits that are all in L1 cache, a probe, it worked, you put it back on the free list. There's like tiny nanoseconds, no cache misses. Whereas the constant allocation to go build a new object does, for C2, it was very obvious. Actually, in AA too, it's very obvious. It burns a lot of memory and it turns into performance. So interning is a thing that wants to happen. And then when you intern, by the way, that fixes all kind of other problems having to do with like performance of recursive tests, of recursive equalities. Where's a good example here? Everyone who does like a meet goes recursive. But if I do I know, do an ISA. A lot of ISA tests. ISA says meet is a T. Okay, what's meet do? Well, we're just looking at meet. When does meet allocate? Well, it turns out if I intern and I recycle memory, meet like never allocates, and it's just like a little tiny thing, but it does go recursive. So if I keep going recursive and recursive, recursive, this kills you if you have recursion. Here is meet again on structs. Okay. What's the struct meet? That's type. Come on. Oh, X meet. I want the struct version of meet. What's struct meet? Well, there's some cutouts for top and bottom. And then there's like all your fields are the same and they're the same length and they have all the same names. And then you meet field contents. What's a field content? Well, that's a type memory pointer. So you go recursively deep cyclic if you don't intern, you will go exponential on the all the different ways that pointer to field to struct to pointer to field to struct or struct field pointer. Those will go exponential in a hurry. So if you intern, then ultimately all the meets start with, oh, you're interned. You're that same thing. Don't recurse. Just get out. You're done. This one line stops exponential search on meet if you're interned. And otherwise, you have to actually, go exponential or stop exponential with a visit bit. And the visit bit means you have to carry visit bits all the way through everybody and test for set and clear, whatever, and deal with visit bits. So the interning saves a bunch. It's not just performance, it saves a lot of complexity in the code.
So you touched on performance. I wonder, was this kind of very tall lattice, because let's say for primitives, for ints, you have the ranges. Do you ever see issues with fixed point iterations like taking long to converge?
Yeah, in C2, I had to put a widening bit. Simple will need it, and it doesn't have it yet. And the widening says I widen an integer only so many times, and then I just give it up. So the classic example is just for loop. For I equals 0 to n, I plus plus in the loop. You know, you're just running a for loop over an array. Well, what's the value of I? Well, it's 0. And then the next iteration is 0 to 1. The next iteration is 0, 1, 2, 0, 1, 3, 0, 1, 4. 4 billion. Okay. So you don't want to fall 4 billion times. So you have a falls in the lattice, a widening operator. And I kept it at 3. You know, you fall 0, 0 to 1, 0, 1, 2, 3 times, give it up. Now x is, you know, I goes to infinity, and I just give you the fat int and done.
Oh, wait, is it something that exists on the lattice structure that kind of shortens the lattice, or it's something in the fixed point?
No, it shows up in the lattice, and then because it's in the lattice, it comes in the fixed point. It comes in the fixed point on phi nodes, which do the merging. They get the widening. Only type integer with the ranges has this problem. Everyone else has a fixed size thing here. Let's stop for a second and go back to the pile of lattices, like here, this one. So if I look at other people who don't have ranges, floats go to, or might we shrink to float 32 top, sum one float, and then float 32, and then you're done. So the floats are 5 deep. Pointers just have nil or not. They're 1 deep plus top bottom, except structs, which go to fields, but each of these fields is itself shallow except for the ints. Memory, 3 deep. Tuples, 3 deep, except each of the types internally has however deep they are. It's just the ranges here where a variation of ranges, as we're talking, yes, expands. So in the lattice in C2, not yet in simple, but needs it, is parallel to the min-max, there's a comma widen count. How many times did I widen you? And phi runs the widening meet step. So the meet is if I have two things and one's inclusive from the other, they take the max of their widens, but if neither endpoint moved, you don't raise the widen.
Ooh, so basically, yeah, you can represent arbitrary range, but then there are these chains of 3 that you can move along.
Yeah.
On that lattice. Okay.
Right. And
like if you try to visualize this, like conceptually, it's pretty straightforward. But if you try to visualize this on a lattice, it kind of explodes into
I have
a lot of different variants.
I have those pictures from the C2 era where I would have a row of ranges of all sizes have its own thick bar. Then there's a widened version of the same row underneath it, and the third widen, and then you're done. And anyone from the first widen that moves an endpoint goes to the second widen stage. But yes.
Okay. So it's maybe not as crazy as I thought. Literally, you have 3 levels. Yeah. On each level, you can have any possible range, and you have transitions from any range.
The code involved is trivial, right? The code involved says endpoints moved, add 1 to the widen. If the max, I'm sorry, it's a little more conservative than that. It's like you take the max to the widens. If the narrow guy didn't move endpoints, there's some rule that says that you had to move an endpoint and be at max, and be the fatter widen, and the fatter widen had to move endpoints. Then you bump widen again. Fine. It's not hard to work out, but it's 2 lines of code, but the diagram on screen becomes this enormous thing.
I like it. I like how you have the precision, but you solve that the
infinite
iteration problem, but then keeping it all within lattice theory. Like it fits nicely. It's not that you have some kind of I don't know, band-aid on the side.
Yeah. Oh, I fought with many compilers in years of yore who failed on these various fronts, and you ended up with an infinite pile of special cases and this and that led to all kind of corner casey bugs and whatever. Stick within the lattice. It's just the meet operator. You don't have any brains, any smarts necessary anywhere else. The lattice just takes it. So I claim this is the way to think about this set of problems in compilers. Okay. Lattice theory. We're approaching 2 hours. I'm gonna claim victory here. If anyone wants to ask a question or do something, now's the time. Here, I'll pull Lattice off the brains.
Yeah, I have a question. I pasted a little photo in the Google
Saw
Docs,
that.
which I think is also wrong, but I that was what I meant by diamond. I think you have an arrow falling from tilde in temp to temp,
Yeah.
which
Okay.
seems like you're forgetting something.
Let me share your
Yeah.
diagram, and we'll look at my simplified version as well. So you have the anti-temp at the top, the X-temp. That's great. You have a twiddle in temp. It should fall to an in temp, which should fall to a temp. You wrote a diamond, but these
Oh, it
all
should fall
go.
to a temp.
Yeah.
Okay, so what is wrong? Yeah,
Let
this
me.
is wrong because
Yeah. I'm not sure how to get side by side with.
hang on a second, that is wrong. I did just take another picture, but
Okay. If you delete and add pictures, that's
yeah,
okay.
this looks better. Hang on a
And these
second.
napkin diagrams, how the hell I did this for many, many years. This is like, yes, I have, like I said, I'm surrounded by generations of old pieces of napkin diagrams where oh, wait, this one. No, wait, this one.
Okay, give me a second here. But
Yeah,
but
yeah.
the insight that I was going to I mean what I think it is union types with null. You could think of
Yeah.
in temp as temp or in, and that's a super type of temp. So let me export that. So this is how I wrote it, but
Yeah.
1 second.
Yeah. You're on
Better
your
diamond.
phone. It's like,
No, I just came inside because I was,
yeah,
I
okay.
figured I'd better so how do I attach that? I say add. Okay, let me delete this guy.
Yep.
Add is insert and then image and upload from computer and better diamond. Okay. So I didn't call it in temp. I just called it temp or
Okay,
null.
slow down. All right, now it appears.
Yeah.
Ah, okay. Twiddle
So
tempered doll. Yes,
yeah.
you're getting closer.
So why
The
would you fall? You have a one that falls from twiddle temp to temp or null
let
in your
me
column,
right.
I think.
Let me fake a little diamond here. So I have this one here, I would say plus temp plus 0, meaning choice. And then on the left here would be the choice temps, and then one below would be the temps without choice anymore. I fell below the lattice. And
Yeah.
then somewhere down here, I want to say, oh no, I have to do temp comma 0, meaning I must support a 0.
Right.
Okay. And then there's a thing on the right here, and this kind of a lattice thing I did for a while where there's on the starting from the top, when I go to the left, uh, uh, I threw away the nil choice. When I go to the right, I throw away the choice of a pointer. I must be this top nil.
Yeah.
Symmetry says I'm a bottom nil, and can't I just get rid of the two nils? They look all the same. Like, why do I have to have two? So can't I just say, oh, this is all like stupid? This is just null. The two like get rid of the thing on the right and make one node on the right. So I did this
Yeah.
kind of a diagram for many years. You'll notice it has some weird problems with not being completely symmetric.
Yeah.
But it's not otherwise terrible. And then the not completely symmetric leads to other issues, as I mentioned in the peepholes,
Right.
get lost or not. But the key observation here is you have to say I'm choice of a nil or I must have a nil. And I go to the
Right.
left, I
Yeah.
throw away the choice of nil. I have a while loop that will never be null. My X, which is unbound just above you, decides he's going to be a 1 and not a 0 from memory. Replace temp with int, same problem. Just replace temp with int. Now I have the same thing with my undefined behavior above. X comes in as the top value. It could be any 1, 2, 3, 4, 5 constant. It might be constant 0. I don't know. I do an if X, that immediately means I care whether it's 0 or not. So if I went to the left, I decided when I loaded uninitialized X, I loaded 1, 2, or 3, but never 0.
Yeah.
And I could be any constant here, and here is oh, load from the stack frame. The stack promises me it'll not be null, but it's random junk. Where in the right, I said, oh, this is weird. And what I really wanted to say is I only got a 0 out of the stack when I loaded uninitialized X from the stack. It was just a 0.
Mm-hmm.
And then the bottom one is, oh, I loaded from the stack and I have to load from the stack and I don't know what I'm going to get. I might get a 0, I might not, but I must load from the stack. Whereas the one on the right here, or this one says, since I'm loading a 0 from the stack, I don't actually need to load a 0. Don't load X at all. It's just a
Right.
0. Constant fold, go away.
Yeah, I think that the way I like that. I mean, I could add two more squares over to the right, and one of them is tilde null, which would be a sibling in the middle, and then at the bottom you'd have a sibling to temp that's null, and that's just an arrow going. I mean, they both exist. It's a trivial to prove that something that might be null and that only might be null has to be null, I think, and you just fall down to null, and that's how you don't have to get rid of it. That's like falling down to something more specific.
I didn't like the X nil versus nil. And in the simple diagram where I'm just looking at pointers or just looking at ints, it didn't matter. It's when I got to both that the lack of an X nil or having an X nil that falls to nil got me the crossing nil bug, where I would cross an int over to a pointer or point it to an int. And when I did my symmetry tests, which was the test that said A meet B, A meet B is meet, but dual A meet dual B is dual A, and so on. Those would always fail if you had the edge from twiddle null or X nil to nil. And that in turn would actually fail in real programs all the time when I would fail my ISA tests and I wasn't monotonic, or I would end up getting pointers into ints as an obvious, you can't have pointers and ints, but I would have pointers and ints. And no, stop. And you would see this weird, funny dead test where I said, if an impossible thing, and in the impossible thing test case, I would say, well, since I know, I've tested X is greater than 1, over here I tested X is less than 1. X is impossible. I can't get here. But what value is X? Well, it turns out to be something bizarre. And then the same thing I would do with temps or pointers and ints. And suddenly I would get this crossing nil bug where in the code must be dead, but I would have both ints and pointers and the code must be dead. And then I'm like, do a load from an int. And then the load code has to handle an int in dead code. And it's like, no, don't make the load code handle an int in dead code. Just stop. How can this be? Right. And so I went back and forth and around and finally, came up with what I got.
Okay, well, just looking at that, I mean, the thing that looks wrong to me is an arrow from temp to temp comma 0, because it seems like that should be the other way around.
So on your picture, you mean?
No, on yours.
On mine. On mine,
well, you don't have arrows, but you have, from there. Is there an arrow from temp to temp comma 0? Like if you were drawing?
There is an arrow from temp.
So that means you're adding
0. This says, I know you're not 0. This says, oh, I don't know. You might be 0.
Which seems like it should be the other way around. In other words, the arrow should go the other way.
No, there's a lattice and I'm falling. I see what you're saying. Okay. Yeah. I consider this to be the most unknowable pointer. I have to compute everything about it. It might be a null. It might not be a null. It could be a pointer to any structure. It's the most unknowable pointer. Whereas the one right above says, I did a test and I learned something. And so go up here to this scopy guy, or this sqarg equals blah, blah, blah. When I do the test on Q, I learn something about Q.
Right. Yeah. Well, I'm not. Okay.
So I claim this Q is
correct, which means to me should be a downward fall. Like I'm becoming more specific. I know something extra. So it should go down.
More specific is up. More general is down.
I believe. Okay, go ahead.
Just different. I think there are different ways people look at it. For me, also, for me, it's more natural to have more specific down. But yeah,
I believe from the center line down, they become more generic, and from the center line ups, they become from more specific to more generic again.
No, they become more and more specific.
That's like the mirror, the mirror image thing I mentioned. It's what it seemed to be doing,
Right. So the issue here is that Cousseau picked a direction that I find to be counterintuitive. And when I was in grad school, I thought, that's stupid. You want the more general things at the bottom. And so I wrote them all that way. And then I went back and forth and found a bunch of people that followed my direction, but the theory guys from Cuso, and that entire crowd of people that took education from that side of things went the other way on their lattices. So now when I talk to theory guys, we always fight with which way is up and which way is down.
That's okay, just to define it. So what for you? You just told me, Cliff, that more specific is up and more general is down. Okay. So I was actually thinking the opposite.
I read here can be strictly more values or
more values. It's more general. Values.
Yes.
But I have a question. Why is plus temp plus 0 more general than plus temp?
No, it's not. It's more specific.
Well, then that's the opposite. It goes like what?
More specific is up. More general is down.
More specific is up. Oh, more general is down. Okay, that's what I wrote down. Right, I forgot already. So then my question is, why is temp comma 0 more general? Oh wait, it is more general. Why is it more general?
Excellent.
More general. Oh.
Here is another viewpoint that maybe helps people. So if I go to that simple lattice here, here's the more general int. Here's the more specific int. Which int is it? It is simultaneously all possible constants. And if you have to meet with a constant, you'll get the constant of whatever constant it is. But this is a more specific because it is more constrained. It's simultaneously all possible constants. Like more constraints make you more specific. To honor the constraint.
Yeah, that's to me that's more general. Right?
Well, this one is I computed a constant. I can't do anything about the computation. I must execute the code to get that constant or get that value.
Okay.
Not value. Here, it's my unbound x from the prior bad undefined behavior x. It is
any.
It is any possible. Hey, yeah, see, Matt. It is any possible. Yeah, and Merry Christmas. And I don't know if probably will not have CCC next week because of Christmas. But the week after, I probably will have to see where it lands on. Actually, let me do that right now. So I'll announce on the video the 3rd. Yes. So no Christmas, no CCC next week. Yes, on January 3rd. That's my current theory, and I'm sticking with it.
Okay. So that's interesting. So your bottom is not nothing. It's not like the empty set. It's the empty set at compile time. I don't know what it is. There's nothing it can be.
That's this one.
Yeah, the bottom.
No.
Well, bottom.
I'm highlighting the top one.
I'm sorry. I thought you said more. Top can be any x.
This is the very problem I have when I talk to these theory guys. We all get ourselves twisted up in a knot. If you consider ints, the set here, to be a set notation,
correct,
and a constant would be a set of 1 elements,
correct,
like the element 1, the element 5, and the bottom would be set of all the ints. Then the top guy is the empty set.
Okay. All right. Now that helps me understand.
Okay.
All right. So I'll think about it again, and maybe I'll send you.
I don't use that notion when I get to more complicated lattices because it's too constrictive on the kinds of things you think about. So instead, like the ranges on ints, the ranges don't work on the empty set versus the full set. So a better version for me is to go to power sets, but that gets too cumbersome. So instead, I go to this more general down here and more constrained up here.
Okay.
The empty set being maximally constrained. There are no choices to be had.
The way I was thinking about it is like when you do type inference and you have subtyping, you'd compute least upper bounds. And here, when you're doing optimization, which is like a later phase of the compiler, you do greatest lower bounds to you want to go down. You want to make.
But I do them simultaneously.
Yes, exactly. I know.
There's not a later phase.
I shouldn't have said
it's done at the same time.
I got you. That's right. But what it's doing is with a proof, I can go down, whereas I can always go up because that's by definition known to be sound. But I have to have a proof to go down. And the compiler says, "Oh, I feel like I've discovered this can only be in this range, so therefore I can assume that this will, something." And then you go down, is what you're doing.
That's a different way to think about it.
And then you do optimization.
So when if I see a meet of 0 and a 1, I'll fall down to a meet of 0, 1. Cool. Hey, fine. But to go up, I have to have a test in the code. And the test lets me cast and say, I'm casting away 0. I'm testing for 0. You're not a 0. So I throw away the 0 choice. Since you were a bool and you're not a 0, you better be a 1. And that's how I lifted you.
Yeah, because
And then
set
you
of
get
all
the,
ends. That's because you're upside down from the way I think. Yeah, basically, I'm thinking UML diagrams
Yeah.
where the arrow goes and your arrows go in the same way from
But
specific
can you?
coordinate.
Bill,
It's just upside down.
yeah, you definitely were describing it upside down from the way
I was
Cliff
describing it
draws it.
upside
But
down.
I think you and a lot of the academia are upside down of the way Cliff draws it.
and
Yep.
when I draw it this way, I drew it because the other compiler people I dealt with drew it this way.
Interesting. Yeah.
This lattice of ints for constant propagation was like compiler theory 101. I don't know, very early in my grad school degree, first semester, this was presented as here's constant propagation, here's a lattice for it. So we're talking 25, 30, 40 years ago. And I went, oh, that's obvious. This is, the set of all integers. This is the empty set of the top guy, and here's the set of one integer. Piece of cake.
Yeah,
No problem.
the same thing happens with trees because half the people draw them upside down and half the people draw them right side
Right
up.
side up.
Whatever
Now,
right side
Cameron,
up
which
is.
one is which?
Doesn't matter because half go one way, half go the other.
Well, they also draw
Okay.
stacks going downwards and then say that they're the top of the
Yes.
stack, even though it's the
Yeah,
bottom of
right.
the picture. It's like,
Yes.
really?
Yes, exactly.
So-
Fine.
So
Fine.
so just the way Cliff draws it though, it's most general, i.e. least knowledge at the bottom.
At the bottom, yeah, exactly.
Yeah, least knowledge. And least knowledge to me means I have less opportunities for optimization.
And that's the way
Because
I
I
think
just
about
don't know enough to do something
Yeah.
safely.
You can't do anything at the bottom of the graph, right? Above you can, below you cannot. Yep.
This makes me feel good about using unknown as my name for the bottom node and any as my name for the top node, which I think
I use any and all because I like shortening.
Yeah.
But any for the top and all for the bottom. Yeah. Like the set of all ints is the full set.
I think Simon would definitely agree with having the same number of letters in every word. Any and all works well.
Well, I do unknown and anything, but I leave the G off.
No, I don't want to type.
What?
You use unused U and K. Now I've seen you use U and K. So he's got 3 letters too. It's just you. Never mind. Fine.
You can always go top and bot.
Yes. Yes. Damn it. I use bot. B-O-T. You betcha. No, none of these have that. I don't put on the picture, but yes, the code says bot. You better believe it. All right.
I can see how you can lift from from this bottom to a specific number using, I don't know, a check, a comparison.
Yeah.
Can you have code that will lift you further up?
Sure. It happens all the time. Let's do that code because I fall over that trap and then like get confused. Okay, here. So if x is greater than 1, x equals 3. And then if x is less than 0.
Okay, yeah, I got it.
Right. What is x? Well, when I do this, I do a cast hidden internally of a range of 1 ... max int.
Yeah.
And then here, of course, it's cast 1 ...
Cast has to be the worst word.
To min ... 0, which turns into a negative range. This turns into my negative thing. So it becomes whatever, just see 1 ... 0. The min is 1, the max is 0, something like that. I'm not doing it quite right, but
it's a null set and it's impossible.
It's an impossible set, yeah. But that puts me at a high value in the lattice. So if I go to the range lattice, where's my range lattice? Here.
It's a possible set. It's just empty.
You get to this formulation.
Interesting.
Where?
It's the inverted. Min is above max.
Right. Min is above max, which is an empty set. Well, I mean, the way I think of it is empty set.
Yeah, right. You would say empty, but you would lose precision if you said empty. You would go to this point instead of this point, and you lose precision.
Do you have any practical use of this precision?
Yeah.
It shows up when I'm doing sparse conditional constant propagation with the click generic keep folding optimizations in thing. The precision there says It's going to be either a 0 or 1, but I can choose later. I don't need to pick now. But that's already good enough to say you have an enum with 7 choices, but I know 5 can't apply, and 2 I'm going to be able to pick from later. So I'm immediately going to throw 5 away, and then I'll deal with the 2 I'm going to pick later when I find out which way it went.
So is it for the case where you're doing optimistic assumption that you later verify?
Yeah. It turns out that I get this out of some peeps as well, but the main one is I have optimistic assumption things happening, and it lets me take an early cut of things that are already known not to be possible. I kept finding C2 didn't have the high order things for a while, and I kept finding cases where I lost something for a stupid reason because of work list ordering. Going to symmetry prevented the random lossage that was die roll based on random work list. And these would show up in hot inner loops of micro benchmarks that suddenly didn't optimize, and then I get bitched at, hey, you didn't optimize it. What the fuck? And I go sort it out. What happened? Well, bad work list ordering. I lost knowledge, but this work list ordering worked. What the hell happened there? And I had to sort out and said, oh, I didn't have this partial knowledge above the table, above the line.
Yeah, I think in my mental model, when I encounter this kind of paradox, it goes directly to the top. But yeah, right. I see it. It gives you some nice properties, but it's harder to wrap your head around it.
It's harder to wrap your head around. I'll agree to that. Doesn't typically require like hardly any more code. It's just like I do, the dual is just flip min and max. It's literally this few lines of code that's set in one line, few characters of code, flip min and max for the dual. Suddenly I have the entire precision on the upper half. Fine. Same for twiddle 32 versus 32 versus this. You probably do split these apart. I mean, you probably do keep this precision for your conditional constant propagation.
Mm-hmm.
You have floats versus doubles. Yeah.
Mm-hmm.
So that piece is there. It's just that this is unusual for the amount of precision involved, and you're probably just going to this. Fine. Well, there you go. I think we're all about lattices for 2 hours, and way more entertaining too. People were like all over the place talking about this stuff. So the int pointer slice instruct was going to become one of these scalar guys, and the improved conjoined lattice I don't have yet. Don't have a picture yet, but that's where it's going to go. And it will let me have function pointers that I can assign null to without getting a type error. Yeah. That was my I'll work on simple and make function pointers happen, followed by stop, can't assign null to a function pointer. That was the driving piece, Cameron, you missed, was can't assign a null to a function pointer because null was a memory pointer, and you can't put a memory pointer in a function pointer. And that was like, oops, wait, back up, stop. What the hell do I do about that now? Fine. Okay,
Well,
anyone else? Anything else?
I would also agree that you can't assign null to a pointer, but that's for a different reason.
I'll not let you use
the
null pointer to go load, store, do anything useful except tests. So it's an error to use a null pointer with a load or store, but it's not an error to have a null pointer in the first place. You just have to check it, and the compiler enforces it. It's an easy problem. This is an easy problem. All right. And Cameron and I are going to go hassle each other on this topic to the end of time. No next week because Christmas, but January 3rd to see who's got over their hangovers by then. All right.